Hello, welcome back to the video lesson for chapter 6.3 for Math 104. We are now going to simplify radicals, and we've kind of been doing it already with the rational exponents, but now we're going to simplify them in radical form. So there's some properties. One is that we can break apart a radical as long as we keep them to the same index. So a times b with the nth root can be written separated as the nth root of just a times the nth root of just b, which I kind of did in one of my, I think in lesson 6.1, just assuming that it was a natural thing. Okay. We can, the second property is when they are in a rational form, this quotient, we can separate the quotient into two pieces because one of them may be able to be simplified. And then just simplifying radical expressions. So we know that they're simplified if none of the factors of the radicand, what's underneath the radical sign, can be written as powers greater than or equal to the index. So that means there's no perfect squares or perfect roots. 2, there are no fractions under the radical sign, and there are no radicals in the denominator. So remember, that means we're going to have to do something about those. I said we're going to get to that, and we're doing that here in chapter 6.3. Okay, so let's use some of those properties to simplify these radicals in simplest form. So I'm looking for square roots because there's no index here. So I know that 30, this is the square root. 32 can be written as 16 times 2. And the reason I did that is because I know the square root of 16 is 4. So I can rewrite the square root of 16 as 4, and then I just have the square root of 2 left. So the square root of 32 can be written as 4 times the square root of 2. Now, some of these get pretty big, so you'll have to use Desmos to find some roots. So the square root of 128, I don't want it to be written as a decimal. I want it to be, I'm thinking of, if you know your squares, like 1 squared, 2 squared, 3 squares, 9, 4 squared is 16, it helps. 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 81. Writing this down and having them handy to help. Sorry, 8 squared is not 81, it's 64. 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144. And the reason I did that is because 128 is actually the square root of 64 times 2, because 64 times 2 is 128. And I know the square root of 64 is 8, because 8 squared is 64. So I can write that as 8 times the square root of 2. Okay. Now, likewise, with different indices, I can do the same thing. So the cubed root of 24, I know the cubed root. I know that 8 is a perfect cube of 2. So, and I can rewrite 24 as 8 times 3. So I can write the cubed root of 8 times the cubed root of 3. And I know the cubed root of 8 is 2. So I've got 2 times the cubed root of 3. I have to leave that cubed root because that's not a rational number. Okay, 4th root. So I need to know powers of 4. Powers of 4. So I know some powers of 4. 2 to the 4th is 16. 3 to the 4th is 81. I know 16. If I look in Desmos, I can see that 48 divided by 16 is 3. So I can write this as the 4th root of 16 times 3. So it's the fourth root of 16 times the fourth root of 3. And the fourth root of 16 is 2. So I've got 2 times the fourth root of 3. So remember, whenever your index is something other than a square root, you need to make sure that you keep that along so that the reader knows. Okay, now we've got some more complicated ones here. So we've got the square root of 27 times x to the 5th. So I've got the square root of 9 times 3, and I did that because I know the square root of 9, and then x to the 5th. So the square root of 9, the square root of 3, and then I'm going to write this as 5 halves because that's easier. So 5 halves is really 2 and 1/2. So the square root of 9 is 3. And then x to the 2 and 1/2 means an x squared comes out of the radical. That's a perfect whole number. The square root of 3 stays there. And then the 1/2 means that I have an extra x underneath the radical that doesn't have a pair. It does, and remember, when it's square root, we're looking for pairs. Okay. I'm going to do the next one without the fractions so that you can kind of see it worked out. So it says the 5th root of 32 times x to the 7. So the 5th root means I'm looking for groups of size 5. I need 5 of the same thing. So I'm just going to write all the factors of 32. 2 times 2 times 2 times 2 times 2. So 4, 8, 16, 32. And then I've got x times x. So I've got 7 of them. 1, 2, 3, 4, 5, 6, 7. That's a lot of 2's and a lot of x's. So for me to simplify this, I need to have a group of 5, and I do. I have a group of 5 2's. That's 2 to the 5th. So that means a 2 comes out in front of my radical. Then I need to have 5 x's. For one x to come out, I have to have a group of 5 to make one x to come out. 1, 2, 3, 4, 5. So I've got 1 x that comes out for these 5. And I've got 2 that do not have enough to make another group of 5. So I have to write them as the 5th root of x squared. Just trying them and doing them will help you feel more confident. At first, it took me a long time to get these, a lot of practice. Okay, cubed roots. So I'm looking for things that are cubed. So I know 2 cubed is 8. 8 does go into 128. Well, let's see if something else does. So 3 cubed is 27. And we already know 4 cubed is 80. 16 times 8 is 108. $128. Okay. Oh, there it is. 4 cubed. Let's just look at this in Desmos and just be sure. 4 to the 3rd is, I don't know what I was thinking there. 16 times 4. It's 2 of those. Okay, so let's go back to my paper here. So cubed root, I have cubed root of 4 cubed is 64. So 64 times 2. And then I've got x, 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 y, y. So we just said this 64 is the cube root of 64 is 4. So I've got that taken care of. And then I've got a 2 that has to stay underneath the radical because it doesn't have a group of 3's. Then I've got one group of x's, 2 groups of x's. So I've got x times x, or x squared And then the y times y doesn't have enough to come out, so y squared stays. Okay, h. So 243 to the 5th. So I need to look at powers of 5. So again, if you go to Desmos and just look at your powers of 5, 3 to the 5th. Oh, it's 243. I got lucky. 3 to the 5th. Okay. So that's cool. I know that the 5th root of 243, I know that one. And then I'm going to write these. So I know the 5th root of 243 is 3. So that one's done. And then the others I can write is x to the 7 fifths, y to the 10 fifths, and z to the 5 fifths. So anything that simplifies to a whole number that's what comes out, y squared. That simplifies to y, 10 over 5 simplifies to 2. 5 over 5 simplifies to 1, so just a z comes out. Now, the 7 fifths is 1 and 2 fifths. So that means an x comes out, but there's an x squared left under the radical. So a 3 comes out, an x to the 1, a y squared, and a z to the 1. And there's just this little x squared, the 5th root of x squared. That's the only thing left underneath the radical. Whew. Okay, now we said earlier that we cannot have radicals in the denominator, and look at all of these. They all have radicals in the denominator. So we have to learn what's called rationalizing the denominator. So to do that, we need to, like for here, we have 2 over the square root of 7. So the square root of 7 means we have to have pairs. And what I can do is, since 7 doesn't have a perfect square root, I can just multiply by another square root of 7, and then I do have a pair. I have the square root of 49, which is 7. And so if I multiply by that for the denominator to be forced to a perfect square root, then I have to also multiply the numerator by the same value, because this has to equal 1. Okay, and then you end up with a radical in the numerator, and that's okay. So let's try some here. So for A, if I multiply by the square root of 2 over the square root of 2, I get the 3 times the square root of 2 over the square root of 2 times 2 is 4. And that is just 2. So 3 times the square root of 2 over 2. Now B, this is the square root of 1 over the square root of 3. And so I'm just going to multiply by the square root of 3 over the square root of 3, which is the square root of 3 over the square root of 9. And I can simplify the denominator, into 3. So this is the square root of 3 over 3. Now letter C, I have the square root of 1 over the square root of 6. I could multiply by the square root of 6. So I get the square root of 6 over the square root of 36. And that simplifies to the square root of 6 over 6. Okay, those were all square roots. Okay, and they just needed to have pairs, and so I multiplied by another one to give it the pair. Now, when you have radicals in the denominator that are an index other than a 2, we have a different ball game here. So for instance, D says 5 over the cubed root of 3. Well, the cubed root, 3 is my index, meaning I need 3 of whatever to come out. And I only have 1 3. So I have to multiply by the cubed root of 3 squared. So that I have 5 times the cubed root of 9, essentially, over the cubed root of 3 times 3 times 3. Because remember, the cubed root means I need to have 3 of them for it to simplify. So this simplifies into 5, the cubed root of 9 over 3. Okay, letter E. I have the cubed root of 4 in the denominator. Well, the cubed root of 4 could really be the cubed root of 2 times 2. So I have 2 things. I just need a third one. So I can multiply by the cubed root of 2 over the cubed root of 2. So now I have 3 times the cubed root of 2 over the cubed root of 2 times 2 times 2. I have 3 of them. So that means I have 3 times the cubed root of 2 over 2. So the cubed root. Okay, let's see if we can extend this further. We have the 4th root now. So I have to have 4 things. So this is going to be the 4th root of 5 on top, and then 4th root of 3x squared. So I need to multiply by the 4th root of something. And so I have 1, 3, and I need 4 of them. So I need 3 times 3 times 3. So on top, I also need 3 times 3 times 3. And then I have 2 x's, I need 2 more. So x times x, x times x. Remember, whatever you multiply on the bottom to create your perfect root has to be on top. Okay, so now on top I've got the 4th root of 5 times 3 times 3 times 3. So 27 times 5 is 135x squared. And then on bottom, I've got a group of 3 and a group of x's now. So my 4th root of 3 to the 4th, x to the 4th becomes just 3x. Let's try one more. We have the 3rd root of 5x over 4y. So this is really the cubed root of 5x over the cubed root of 4y. And that's really the cubed root of 2 times 2 times y. So I have two twos. I have 2 twos. I just need 3. So I'm going to multiply by the cubed root of another 2 and then 2 more y's. So the cubed root of another 2 and 2 more y's. So in the numerator, I have the cubed root of 5 times 2 is 10xy squared over the denominator is the cubed root of 8y cubed. And we did that on purpose. The numerator is just the cube root of 10xy squared over the cube root of 8 is 2. And the cube root of y cubed is just y. So the rationalizing business gets a little tricky. And that is all for lesson 6.3. Catch me back for another video, some more extensions here.